So now, okay, as I mentioned that if Eilenberg-Moore category, because the Eilenberg-Moore category uses the algebras, so-called algebras, T algebras, A comma alpha. So this became more popular and it was more useful because all algebraic categories could be recovered from our original from the category of sets just by using certain appropriate monads. However, the Kleisli construction never got widespread recognition. So, I mean, just to highlight this, I'm going to write down a definition which is, I mean, useful but unfortunate, like it's biased towards Eilenberg-Moore. But before I explain that, let's talk about the category of adjunctions. Okay, so given a monad T on C, we define adjunctions corresponding to this monad T as the category whose objects are adjunctions which induce T. Adjunctions inducing T and whose morphisms are functors from D to D prime, yeah, let's call it K, such that the two diagrams commutes. That the two triangles in the diagram, let me write them properly. So this is C, okay, then this is D prime. So C to D there is F, then there is G, then there is F prime, there is G prime. Yeah, this is a left adjoint, this is a left adjoint. So functors at this place from D to D prime which commute. Okay, so what does that mean? I K composed with F is equal to F prime and G prime composed with K is equal to G. Okay, so here I want to give you a note that we expect, I mean we require strict equality and not isomorphism. Okay, so over here we are not saying that Kf is naturally isomorphic to F prime. That would be problematic. We want something up to equality. These functors should commute. And this is a very strong condition. Yeah, I mean, imagine what's happening here, that there are, like C is the base category that's given as part of the data of T. Because T consists of the endofunctor T from C to C and two natural transformations. So therefore we want this functor, the morphism between these adjunctions, to commute with both left and right adjoints at the same time. Okay, so now we have obtained a category. So what is the role of the two constructions that we obtained so far? The Eilenberg-Moore construction and the Kleisli construction. So there is a theorem that FTGT, yeah, the Eilenberg-Moore adjunction is terminal while the Kleisli construction is initial in the category of adjunctions. Okay, so these two constructions, which two people thought at the same time, they were polar opposite of each other. Okay, I mean, what do we do here? I'm not going to give you an entire proof. Now you should be capable of filling in the details if I give you the right ingredients. So sketch is, we describe the EM comparison functor. EM stands for Eilenberg-Moore. So EM comparison functor will go from D to CT. Yeah, what does this functor do? If you are given any object D, so you imagine that this D prime in this upper triangle, that D prime is CT. So if there is an adjunction which induces the monad T, then we have to map that D into CT in such a way that this everything commutes. Okay. Any guesses? So this is defined by, I want to define K on objects. What should it be? Look at the triangle. You want to describe an algebra. Yeah? Look at this triangle. So you want to describe an algebra on some appropriate object. You only know object D, but you want an algebra structure defined on an object of C. So which object? The only thing you can do. What is that object? No, not identity. D is in D, category D. Which adjoint? Left adjoint has landed us inside D. We have to use the GD, very good. And GD with what algebra structure? No, you only know one object in category D. So you only know one morphism for sure, that is the component of the natural transformation epsilon, the co-unit. So you know epsilon sub D, but of course that's a morphism in D itself. What is epsilon D from? Epsilon D is from FG D to D. Now you have to apply G on it so that you will land inside GFG to G, GFGD to GD, which makes sense now. Okay, so this is the morphism, and K of D to D prime is just GG. Yeah, I mean, you have to do the only thing possible. There is no other option here. Okay, and you have to verify, yeah. This verification I am leaving as an exercise. You have verify the commutativity properties. Then the Kleisli comparison functor. What should be the source category of this functor? C lower t, correct. So L from C lower t and 2D. That is what we have to define. So what do you have to verify? Like for EM comparison functor, you need to verify that this is indeed a morphism and this is the only morphism. There can't be any other morphism because it's a terminal object. So existence and uniqueness. We are giving existence, you verify uniqueness. And the Kleisli comparison functor also we are trying to give existence. Now tell me what should be done. Defined by L and L of A. FA, can you define FA? Yes. I mean, F is the second part. Yeah, I mean, I was confused between this. But what diagram you have? Like D is replaced by C lower T and D prime is replaced by C lower, by D and F and G. So this is correct. And then L of the wiggly morphism from A to A prime. This is F. What should we do with this? We have to, of course, start from FA and we have to land in FA prime. So what things can you do? The FF is always going to go from FA to, think about it, FGFA prime, FTA prime, which is FGFA prime, and then from here to here, what do we have? Epsilon sub FA prime, correct. So this is the only thing we can do and this is the answer. Okay, again here verify that this is the only, this is actually a morphism in the category of adjunctions over T and it is the only one. Okay, so Kleisli and Eilenberg-Moore categories, they have a special position in this category of adjunctions. Yeah, but as I mentioned, this EM construction is going to gain more importance. But let's talk about some limits and co-limits. So in general, I mean, this minimalistic construction doesn't allow passage of lot of things. So therefore, in general, CT has few limits, even if C has, yeah. I mean, co-limits are going to be preserved, yes, and only those co-limits which C has. Yeah, you understand this? Because there is an adjunction, so FT must preserve co-limits. Oh, actually that's, yeah, it must preserve, but that doesn't, yes, that doesn't necessarily guarantee, has few limits and co-limits in general, but it can be shown that CT has co-products if C does. Okay. However, for the Eilenberg-Moore construction, we have another result. So GT, and this result is more up our along the lines of our discussion about algebras. So the forgetful functor from algebras to the base category, that one creates all limits which exist in C. So, we have seen such a thing before, if you remember, the category of groups and category of sets. The forgetful functor from category of groups to sets, that does create all the limits. Yeah, so therefore category of groups is complete. Yeah, we have seen this, like every create means what? Whenever you want to construct some kind of limit, then you construct that limit of underlying sets in category of sets, and then you appropriately give it a group structure. Yes, that's what we are saying here. Okay. Moreover, if T preserves co-limits of shape J, then G creates them. Okay, so now this is a conditional statement. Yeah, what it says, that the endo functor has to preserve something, then only G will create it. Then only is also wrong. Then G will create those co-limits. Okay, so okay, so this is something I wanted. I mean, I'm giving these things without proof. I just wanted to give you an idea of how monads work, and you have seen such proofs already. Yeah, how to show that something creates limits, how to show that something preserves limits. You have already seen enough proofs of that kind. Okay, so now this becomes an important definition. It says that, so say that an adjunction, this is arbitrary adjunction, yeah, there is no monad in this picture right now. Is monadic. Any guesses? When will it be monadic? If up to equivalence D is the category of CT, where T is the monad induced by this. So it is the category of algebras. Okay, if it is the category of algebra. So is monadic if the EM comparison functor K from D to CT is part of an equivalence of category. Okay, understood this part? That up to equivalence, D is the category of algebras, T algebras. That's all we need to check. Okay. I mean, there is also a slight relaxation of this. More generally, okay, say that a functor G from D to C is monadic if it has a left adjoint F from C to D such that the adjunction is monadic. I mean, it's an abuse of language, that's all. We are saying that an adjunction is monadic, but we don't have to write down the entire adjunction. It's sufficient to give only 1/2 of the adjunction. You can figure out the rest. And then we say that this property says that this is monadic by extension. Okay. Okay, so one important thing which we could have seen earlier, maybe G epsilon sub f was an important functor. You remember? So there is a note which will motivate our discussion further. Okay. So this is a note. So the Eilenberg-Moore adjunction is essentially characterized in the category of adjunctions by the fact that for each B in D, the diagram, okay, let me write this diagram. So on one side, like we have too many F and G's, yeah, and this can actually be written as a square also, commutative square. One side we have Fg epsilon sub B, and the bottom part is epsilon sub FGB. Yeah, there are two different ways, and here I am just taking epsilon B. E is a co-equalizer. Is a co-equalizer together with some, with nice properties. You can understand it is actually a commutative square. Yeah, we have Fg epsilon B, then we have epsilon sub FGB, then we have epsilon sub B, epsilon sub B. And why does this thing commute? Because epsilon is a natural transformation. This square commutes because epsilon is a natural transformation. That's all. Okay. So, but it is a co-equalizer with nice properties. So we have to know what these nice properties are. Then perhaps we can use this to test monadicity of a given functor. Okay, so before I get into this next discussion, I want to remind you that any isomorphism, yeah, any isomorphism is preserved by any functor. All of you agree? Yeah, whether a functor reflects isomorphism, which is like conservative property, that is a question. But isomorphisms are definitely preserved by functors, because isomorphisms are given by identities or equations, and equations are always preserved. Equations are all about composition, so they are preserved. Similarly, you might remember that at once we talked about idempotents. So idempotents are also preserved by, idempotents are any morphisms whose square is itself. So E square equal to E, that kind of morphisms. Okay. So they are also preserved by any functor. You agree? Because it's equational. Similarly, yeah, splitting of, so splitting, I think we also did like splitting of idempotents. Idempotent splits, you remember? It's if E is an morphism which is given by this. Let me do it as a side thing. Yeah, so suppose A to A E is an idempotent, then what is a splitting? Okay, have we never talked about this? So it is a pair, yeah, F and G, such that, yeah, a splitting of E is this pair such that G composed with F is E and F composed with G is identity on B. Okay, so this is a splitting. And what I want to say that this splitting is also preserved under any functor, because again it's equational. So everything that is equational, that is preserved. In fact, this F, yeah, I mean, can you tell me which one of the F and G's are is a monomorphism and which one is an epimorphism? G is a mono. G is a split mono. Yeah. So G is a split mono, and I think we can obtain these F and G by this. Yeah. So this B to A, this is a mono, and then I have two maps, identity on and this is G. This is an equalizer diagram. Yeah, because E is GF. So GFG is equal to G. And this is the best possible solution. So this is called a split equalizer. I want to say that this is an absolute limit. This particular equalizer is an absolute limit, which means any functor preserves it. And that just happens because it's given by equations. Okay, so it's an absolute limit. Dually, you can say that F is an absolute co-limit of the same diagram, E and 1. So absolute limits and absolute co-limits, just like isomorphisms, are preserved by every single functor. Any questions about that?
What is absolute? I mean, it's just a limit, right?
It's a limit, but it's preserved by any functor. This is happening inside a category, but if you take any functor leaving this category, then this particular diagram will be mapped to another diagram, which is going to be a limit diagram. That's absolute, yeah, which means preserved by every functor. Okay, now keeping this thing aside, now we can come back. This particular co-equalizer, I said it had nice properties. So let's look at those nice properties. So I'm going to give you a definition. So this is a split co-equalizer diagram. That's the definition. So the data is given by this diagram. There is F, there is G, then there is B, and this H. We are not even going to claim anything yet. Yeah. I just have lot of maps, T and S. Okay. So this is any such diagram satisfying some equations. So of course, I want it to be to satisfy HF equal to HG. I have not claimed that it is the universal, it has the universal property, but HF has to be equal to HG. Then HS is equal to 1C. Then GT is equal to 1B. And finally, FT is equal to SH. Lots of equations. The simple way to remember this is that the outer rectangle it commutes. Outer rectangle, like you can start from B and then you can come back to B in two different ways. Outer. One is first take T then F, or take H and then S. So that commutes. Of course, it's co-equalizer, so HF equal to HG is not a problem, and the splitting is given by for G. Yeah, I mean GT is a split identity for B, and HS is identity for C. That's splitting. So in particular, you can conclude something about SH. Yeah, that's an idempotent or not. Yeah. Okay. Okay. So now we are going to so simple proof. Yeah, that H is indeed the co-equalizer of F and G. Yeah, simple proof. Okay, so suppose we are given this K from B to D, and it satisfies Kf is equal to Kg. Then what do we have? Well, we start with Kft, that is Ksh. Ft is Sh. But Ft is Kft is also Kgt. Maybe I should write it in opposite order. Ksh is Kft, but Kft is Kgt because Kf is equal to Kg, and Kgt is equal to K. Okay, so therefore K factors through H, and uniqueness of this factorization follows from the fact that H is split epi. Okay, so therefore, if you are given very strong conditions like these four equations, then indeed H is a co-equalizer. But this is a split co-equalizer. And what is speciality about this? Speciality of this? It's an absolute co-limit. Any functor will preserve it, everything is given by equations. Okay. Now, let me just mention that. Yeah, so split co-equalizer is an absolute co-limit. Okay, which means any functor will preserve it. Okay, so can you see, I mean, our discussion was motivated by this particular diagram. I'm going to claim that this diagram is indeed a split co-equalizer diagram. Okay, so let me write that diagram again. So Fg, Fgb, then Fg epsilon b, epsilon sub Fgb. While I am writing this, can you think of what the splitting should be? Can you think of a splitting for epsilon b? Does there exist a splitting or not? Not in general, right? However, Yeah, I mean, I wrote the diagram again. I could have simply shown you the splittings in the above diagram. I wrote the diagram again because I wanted to add another G everywhere. And now notice something. I added G everywhere. Now this becomes a split coequalizer diagram. Because for G epsilon, what is G epsilon sub B? Does it have a splitting from triangular identities? Eta, yes, eta sub GB. Correct. Okay, and in the reverse direction, in from GFGB to GFGFGB, what do we have? It's eta sub GFGB. Okay, so using all the diagrams that we have drawn so far, this indeed you can check to be a split coequalizer diagram. Okay, so this one will be identity eta sub GB composed with followed by G epsilon B, that will be identity. Then this outer rectangle, yeah, from GFGB to GFGB, two different ways, that will commute because eta is a natural transformation, and I think no, epsilon is a natural transformation. Wait, why does it outer diagram commute?
Somehow we are using a triangle.
Yes, we are using the triangles. Yes.
So like that triangle is, it's actually going to GFGB and from GFGB to again it's going. So
Yes, GFGB to eta sub GFGB and followed by this. The outer one has to commute. That is the reason I can't think of. The inner one is easy. Yeah, because this G is coming out. So FGB we have that we can ignore, and G epsilon and eta sub G, that commutes. So that is just triangular identity, this inner part. Yeah. This one is also another triangular identity. Why does the outside thing commute? Okay, do it as an exercise. Yeah, let's leave it. Let's not spend time on this. But this is a, yeah, so this is a split coequalizer diagram. You should be able to verify this. Okay. Okay, so motivated by this, actually we have a new definition. Okay, the definition says that given a functor G from D to C, say that this particular diagram, diagram of parallel arrows in D is G split if there is a split coequalizer diagram GA, GB, GF, GG, and then some C. Yeah, it doesn't matter like whether this C is in the image or not, that's not important, but some S and some T. There is a split coequalizer diagram in C. So when you take this parallel pair of arrows, when you map it under G, then it becomes a it has a split coequalizer. Okay, that's what we have written here. Okay. There is another property that this particular diagram has. So let me write another definition. So say that a parallel pair of arrows is reflexive if there is R from B to A such that it is common splitting for both of them, such that FR is equal to GR is equal to 1B. Okay, so this pair is reflexive. It actually represents reflexivity of the relation. And that's why we are writing this. Okay, so reflexive co-equalizer is the co-equalizer of a reflexive pair. Yeah. So we are given a reflexive pair, take its co-equalizer. Fine. So, so take FG and this parallel pair with FG epsilon B, and over here we take epsilon sub FGB and get down to FGB. Yeah, this is reflexive. Yeah, what is the common splitting? F eta sub GB. Okay, so this is indeed a reflexive diagram. In fact, yeah, we used long time ago, let me try to figure out where that one was. We proved a result which said that all limits can be constructed using products and binary equalizers. Yes, this is the theorem. All small products, all and binary equalizers. Yeah. So this is the diagram. Yes. So this is the diagram that we constructed at that point. So this is in fact a co-reflexive pair. This F and G, that's a co-reflexive pair. So the actual modification of this statement should be that all small limits can be computed using only knowledge of small products and co-reflexive equalizers. Okay, co-reflexive equalizers. So because this diagram is, well, I know the answer, but I am leaving this for you. Figure out what is the common splitting. Okay. Let's go to this. Okay, so reflexive co-equalizers are like this. So you saw that the diagram that we started with, yeah, this particular diagram, that is both G-split co-equalizer and it is reflexive. This pair of morphisms FG epsilon sub B and epsilon sub FGB, that's both. And these two different properties are going to give us two different versions of tests for monadicity. Okay, so let me write down. This is called Beck's monadicity theorem. Beck is the name of the person who proved. Yeah. So Beck's monadicity theorem says that there are two versions actually. The first one is the precise version, and the second one, just like adjoint functor theorem, yeah, general and spatial. So here precise version is an if and only if condition, the crude version is just a sufficient condition, and in different situations you use different versions. So the precise version says that G from D to C is monadic if and only if, yeah, first of all, G must have a left adjoint, otherwise we can't even talk about a monad. Okay, so G has a left adjoint, and G creates co-equalizers of G split pairs. Okay, so creation of co-limits, we are talking about it for the first time. We generally talk about creations of limits. So G creates co-equalizers of G split pairs. So that one particular diagram is so important that if you ensure this, then you get an if and only if condition. Yeah, so that's the precise version, and the crude version. So crude monadicity theorem, it says that G from D to C is monadic if and only if G has a left adjoint. We can't leave this, sorry, not if and only if G has a left adjoint, then G is conservative. What does that mean? Yeah, i.e. reflects isomorphisms. And G preserves reflexive co-equalizers. Okay, so this is a sufficient condition, but not a necessary condition. Okay. And as is our pattern now, I'm not going to prove it. Both theorems can be proved simultaneously, essentially. Only one part, like precise version, has a forward implication that has to be proven differently, but both theorems can be proven. You can check the proofs in Maclean's book, Categories for Working Mathematician. What I'm going to do instead is I will give you some examples. I mean, we'll do one example properly, and that is the example that we already know. Yeah, this U from groups to sets. Yeah, obviously it has a left adjoint. The free group functor. So, and it is conservative. It's conservative. So see, if there is a bijection between two groups, yeah, if there is a bijection like a bijective group homomorphism, then it must be an isomorphism. Yeah, we are saying trivial things. So it's conservative. So what do we need to prove? That it preserves reflexive co-equalizers. Okay, so for that you are going to need a fact. Okay. The product, like binary products, commute with binary co-equalizers. In the category of sets. Yeah, so you remember we talked about commutation of limits and colimits with each other. Yeah, and we also use some word, a doctrine, logical doctrine, like what commutes with what. So this is again a fact. Just like we know that finite limits commute with filtered colimits in the category of sets. Okay, so binary products commute with binary coequalizers. If we know that, then how can we use it? So we need to show that U preserves reflexive coequalizers. Okay, so let G, H, F, G be a reflexive pair in the category of groups with coequalizer. Coequalizers do exist. Yeah, we know that. Category of groups is complete and co-complete with coequalizer H to K. Yeah, let's call it little h. No, yeah, in sets. Okay. Now, so we are given one diagram. So G, then FG, H and K. This is one coequalizer diagram. I have another copy of the same coequalizer diagram and I can take the products in individual components, and that by the fact it will still remain a coequalizer diagram. So now observe this, what the diagram that I am creating is this, H cross H and then K cross K. Okay. So what do I have here? F cross F. Everything is happening component wise. H cross H over here, little h cross H. But at the bottom level, I also have the original diagram F, G, and from G cross G to G, what do I have? The multiplication map for group G. Then from here, I have the multiplication map for H. But K, I don't know yet. Yeah, whether K is a group or not. So I think I said something like it's a reflexive pair and then we are supposed to take its coequalizer in the category of sets. Okay. Does this rectangle commute? Like there are two rectangles here. Do they commute? MH composed with F cross F is F composed with MG. Yeah, that's true because MH and MG are group operations and F is group homomorphism. So it commutes. Yeah, similar with G. Okay. Now use that fact and then you can observe that there will be an induced map over here. It will be the factorization through the coequalizer. So what I am saying, okay, let me say that H composed with MH composed with F cross F. Yeah, okay, let me write it. H composed with MH composed with F cross F is equal to H composed with F composed with MG, which is same as H composed with G composed with MG, because it's a coequalizer there, and this is equal to H composed with MH composed with G cross G. Yeah, Yeah, everything is clear here. So therefore, H composed with MH co-equalizes, weakly co-equalizes F cross F and G cross G. So therefore, there should be a unique factorization through the co-equalizer diagram, which is what we will call MK. Okay, so this MK is going to be our group operation for K. I think I am making some mistake here. Yeah, the crude monadicity theorem that I have copied, it's not right. I think it should be creates reflexive co-equalizers. I should make a change here. Yeah, I mean this should be creates. That's what we are trying to prove. I copied something wrong, but that's what we are trying to prove, that it creates co-equalizers of reflexive pairs. Let me write it properly. Okay. And that's what we are trying to prove here. Fine. So now we have obtained this multiplication for K. And why does any equation satisfy? It gets satisfied. Yeah. Like for example, associativity of this MK. MK is a binary operation that is associative. It will follow from associativity of MH. Similarly, like identity exists for MK, that will follow from identity exists for MH, and so on. Everything will just follow from this co-equalizer diagram. Yeah, you have to write more complicated equations, but everything is just here. These are all finitary algebras. Group is a finitary algebra, the operation is binary, then inverse is unary, and identity is nullary. So in fact, like this, so use equational properties of MH to conclude the same for MK. Okay, so therefore, so that MK is indeed a group homomorphism, and this is the way we have concluded the verification that U creates co-equalizers of reflexive pairs. Understood? And the same proof will work when I replace groups by any algebraic category, finitary algebraic category. Yes, so same proof for when GR is replaced by alg for any finitary algebraic category. Finitary means all the operations should be finitary. For example, complete lattices. Yeah, we saw that last time. That is not finitary because we ask for arbitrary joins and arbitrary meets. Yeah, that's not finitary. Everything, like you are given finitely many inputs and you give one output. Okay. Another example, like we have done one example. Okay. Another example will be about a reflection. So if, what is a reflection? Please remind me. Inclusion of a full subcategory has a left adjoint. Okay. So any reflection is monadic. So for example, we are given this particular, like what is important? I from C prime to C, this is our inclusion functor, and then it has a left adjoint, okay. Then, so which functor is monadic here? What are we talking about? The right adjoint. Yeah, I mean, basically the inclusion functor is monadic, okay. C prime is a full subcategory, yeah, that's also part of the definition. So if A to B is I split in category C dash, then this FG it is I split means what happens? Like I embed it inside and then I get this diagram. Yeah, I split means once you map it into the target category, then the diagram has a split coequalizer. Okay, we have seen the definition of split coequalizer. Now there are certain things to argue. First of all, I was highlighting the fact that C prime is a full subcategory. And that fullness is useful to conclude that T is in C prime. Yeah. So since C prime is full, T is a morphism in C prime. Okay, what else? We also have to conclude that object C, capital C, is in C prime. How do we get that? Exactly. So C is the splitting of which one? Which idempotent? SH. Of the idempotent SH. Yes, from IB to IB. Okay. Yeah, and hence S is in C prime. Why? No, fullness will not give you that S is in C prime. You just have to talk about the splitting now.
Yeah, I mean, like, it's the identity.
Uh-huh.
That trigger.
No, it's not identity.
The
SH is a morphism with domain in C prime and codomain in C prime. We haven't yet said anything more. The splitting, if you remember this red note that we had earlier, the red note said that a splitting of E is this, and this is an absolute limit. And dually there was a co-limit condition. So try to use one of them. And reflective subcategories are closed under limits. Okay, and hence, okay, so C is an object of C prime. So whatever limit, closed under limits means whatever limit you compute in the parent category, the same limit exists in the subcategory. Okay. So therefore, we have used the precise monadicity theorem over here to conclude that any reflection is monadic. You can of course prove it directly, and I will give that as an exercise. That prove this directly. You have to have some hands-on experience. Some more examples, like if I take top and then sets, yeah, from top there is a forgetful functor and it has a left adjoint D, discrete topological space. Yeah, so this is not monadic. Yeah, this is not monadic because what will be UD? UD will be just one subsets, its identity. You take any set, discrete topology, forget about the topology, you get back the functor. And this is the monad induced by this. T is identity, then eta from like eta is appropriately one sub one subsets, and mu is also one sub one subsets. Nothing is happening anywhere. And obviously, yeah, I mean, identity monad is not going to generate category of topological spaces. Right? So it can't be monadic. The algebras for identity are just going to be itself. Yeah? The category of algebras for this trivial monad is just the category itself, isomorphic in fact. But if you take this particular functor, which is the forgetful functor, this is monadic. This was somebody's PhD thesis, I think, and this particular result. Okay, any questions so far?
So, whenever we are talking about the common splitting.
Common splitting.
So, does there exist a condition on the morphisms if and G such that the common splitting will occur? Like, I'm asking, like, I mean, is it so? If the common splitting is there, then we have this.
Yeah.
But is there any case where,
like, do you want some conditions for reflexivity?
Yeah. So, like, I mean, for common thing, like, if I
No,
have
I don't
G,
know. I don't know. Here, like in this proof, you just have to test for
so
that.
In this case, it's like it's given that
Yeah.
if it is common, then these things.
Yes, but otherwise I don't know.
Because I think finding common is kind of.
Yeah, but here, like, you can actually see in 2 we verified that. Yeah, that it was on no, not in 2, in 1 we verified that. The application was fairly straightforward. It was given to be a reflexive pair. In fact, we did it for anything essentially.
So yeah, I mean, like, for here, one thing that was following, like, we had H and G to H we had.
We just had a pair. Actually, we showed it for more generally. Yeah. Any other questions? Okay. So we should talk about now. Yeah, we should talk about some categorification business. Okay, so what is categorification? It simply means that we start with some concept which is algebraic. Yeah? Let's say a simple example is of a binary operation, and we categorify it, which means we take one particular, like the operation, the functions become functors. The elements become objects, and equalities become isomorphisms. Okay, so that's the idea, basic idea of categorification. Right, so next time we are going to look at categorification of monoids. a binary operation will be generalized to a bifunctor, like categorified to a bifunctor. The identity element will be a specific object, and the multiplication, no, what else do we need? Yeah, the equalities, that equalities of operation, like associativity is up to equality, right? M into N into P is M into N into P. Now those equalities will be replaced by natural isomorphisms, but we have to keep track of lot of data. So the real problem in categorification, the real complexity arises from keeping track of all these natural isomorphisms. So there are different names for them, and there will be some coherence conditions which those natural isomorphisms have to satisfy. And this is what we are going to do next time, because we also want to study enriched categories. So categories enriched over something. So the home sets we have been talking about locally small categories. What does that mean? That the home sets are sets. The collection of all morphisms form a set. So actually you can also generalize it. You can ask my home, the collection of all morphisms, that can be algebraic construction. So for example, it can be an abelian group. But then the composition of morphisms, whenever the home sets are abelian groups, like they have some addition operation, then the composition of morphisms should also be bilinear. We have to capture this notion. And in order to capture this notion, we have to first talk about symmetric monadal categories. And from there, we will use enrichment over certain symmetric monadal categories to understand these situations. Okay, so that's our goal for next time. Let's stop.